Greetings to everyone and welcome to this video on my YouTube channel. Today in this video we are going to be starting a new series of the topic known as curve sketching, and we all know that in curve sketching there is an important element known as the theory of limits. So today we are going to deal with the study of limits, after which in the subsequent tutorials we shall get into the use of limits in curve sketching. So I believe that before the end of this tutorial video you shall move from the beginner that you are now, or probably to an expert in curve sketching, or in the study of limits, evaluating limits, with I myself, Sir Godwill Yakum. I'm going to start by giving you the program of the program of today, what we are going to be looking at, and I'm going to title this part 1 because part 2 is going to come up from now, between now and 24 hours. Part 2 is going to come up, which will have to do with the use of limits in evaluating infinite branches, meaning asymptotes, use of limit to find asymptotes of curves, the use of limit to define the derivability of a function, and the continuity of a function either at a point or at an interval. We shall also look at the use of limits in determining the relative position of curves, either a curve, two curves, or a curve and a line. So but in part 1, these are a list of what we are going to be looking at. We'll start first of all with the definition of limits, and then we'll talk about the existence of limits. Then we'll proceed to mathematical operations on limits. We'll then move to indeterminate forms of limits, properties of limit, evaluating limits, and finally removing indeterminate forms of limits. So without wasting of time, we're going to begin with the first article, which is the definition of limits. Consider a function f dependent on a variable x. As x tends to a, if f of x tends to L, that is, it means the limit as x tends to a of f of x is equal to L, because as x tends to a, f of x tends to L. So the limit as x tends to a of f of x will be equal to L, which in direct substitution is f of a. Now we proceed to discuss the existence of a limit. When do we say that a limit exists, and when do we say that a limit does not exist? Now there exists a limit as x tends to a of f of x if and only if the limit as x tends to a from below of f of x is equal to the limit as x tends to a from above of f of x, which is definitely equal to f of a, and f of a being equal to L. So for us to say that a limit exists at a point, the limit of a function exists at a point a if the limit of that function exists before the point a and after the point a and is equal. Now if the limit exists before and after the point a but is not equal to f of a, we now say that the there is a continuous extension at A. We're going to see more about continuous extension in part 2 of this topic on limits, when we shall be talking on the continuity of a function. So for us to say a limit exists, it means that the limit exists to the left and to the right and is the same. Now let us move on to talk on the properties of limits. Alright, this is the first property. We have that the limit of a sum, the limit of a sum or the difference of two functions is equal to the sum or the difference of the limits. That is the first. So the limit of f of x plus or minus g of x will be the limit of f of x plus or minus the limit of g of x. So the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits. Let's go to the second. Or the limit of a product is the product of the limit. We move to the third, which will talk about the quotient. The limit of a quotient is the quotient of the limits. Alright, here we have something exponential. F of x to the power n is the limit of f of x, all that raised to the power of n. Now the limit of a certain m raised to the function now is equal to the limit is equal to m raised to the power the limit of the function. So when you look at all this, there's something you can already remark. You remark, note that the limit follows the function. The limit follows the function. So if you have a constant raised to the function, the limit will apply only to the function. Forget about the constant. So the limit always follows the function. Finally, we have the limit as x tends to a of 1 over f of x is equal to 1 over the limit of the function. So the limit always follows the function. We proceed. We are still on the properties of limits, and now it's important to note down something. If for every x, f of x is greater than or equal to g of x, this is a case study. If for every x, f of x is always greater than or equal to g of x, then if the limit as x tends to a of g of x is positive infinity, then the limit as x tends to a of f of x must also be positive infinity. I think this comes to make sense, because we begin to notice that in this case we are saying that f of x is bigger than g of x or equal to, meaning that g of x is the smaller function. So if the limit of the smaller function is positive infinity, then talk less of the bigger function, which will also be positive infinity. On the other hand, if the limit of the bigger function, which is f of x, is negative infinity, then it means that the limit of the smaller function g of x will also be negative infinity. So that's the first case study. Now it's important we look at the mathematical operation on limits. Mathematical operation on limits will have to do with the addition, the subtraction, and multiplication, the division. But on a special note, we're going to look at addition, multiplication, and division. So we'll start with the limit of a sum. I'm going to represent it in a table. It's like a summary of the limit of a sum. If you have, remember I said the limit of a sum is the sum of the limits. Yeah. So what if you have the first function f of x, and the limit of f of x is a certain L, and the limit of g of x is positive infinity. So let me represent this on a table so that I give you all the possible outcomes. Alright, so in the first column, row 1, column 1, you have the limit as x tends to a of f of x. Go down to row 2, the limit as x tends to a of g of x, and finally in row 3 you have the limit as x tends to a of f of x plus g of x. So now if the limit of f of x is L and the limit of g of x is L prime, then f of x plus g of x, in the limit of that will be L plus L prime. You just add the two limits. Now if the limit of f of x is L and that of g of x is positive infinity, then we are adding something positive to positive infinity, which remains positive infinity. On the other hand, if the limit of f of x is L and g of x is negative infinity, then upon addition we are going to have negative infinity. And this continues all the same till the last column. In the last column we have that the limit of f of x is positive infinity and the limit of g of x is negative infinity. If you want to evaluate this, you're going to have infinity minus infinity, which is undefined. Take note, when we get to the indeterminate forms, you're going to see one of them being infinity minus infinity. Remember, infinity is not a number. Infinity is an actual number. So infinity minus infinity is undefined. We cannot tell what number it is, because we don't know the infinity we are talking about, but we only know we are talking about a very large number, so we can't tell what exactly the limit is. So now we are going to continue with the limit of a product. Alright, the limit of a product, I'm going to have represented it just in 5 columns and 3 rows as well. So everything remains the same here, except that I have made an error in the limit as x tends to a of f of x being L and that of g of x being L prime. Then the limit as x tends to a of f of x plus g of x will be L times L prime, not plus. That's the error I've made there. Is L times L prime Alright, so everything being equal, you notice in row 1, okay, look at column, the second to the last column, column 4. Very good. In column 4, the limit of f of x is 0 and g of x is positive infinity. So we have 0 times positive infinity, which is undefined as well. It's undefined. So we are coming down to, well, we have started seeing some limits that will give us a certain number that we cannot actually tell what the number is. So that's why we say it is undefined. It's indeterminate form. We cannot determine the exact value of that limit. Now we're going to continue. We'll end up with what, the limit of a quotient. Alright, the limit of a quotient. This is how we have it. If provided the limit of f of x is not 0 and g of x is 0, then you have something divided by 0, and something divided by 0 is undefined, right? Any number divided by 0 is on your calculator will give you math error. So that is, you're going to have it as a positive or a negative infinity. Now it depends, the value of this infinity or the sign of this infinity depends on the sign of the limit of f of x. So now provided f of x, the limit of f of x is not 0, then now the limit of let's say if the limit of f of x is positive, like let's say 3 or 5, then when the limit of this product will be positive infinity. But in case let's say it is negative 5, then the limit of the product will be negative infinity. Alright, so you proceed to now see that the limit of the product of f of x and g of x, where the separate limits themselves give you 0, 0. You can see that in column 5, 0, 0, and the limit of that product is undefined, so it is indeterminate form. Equally, where you have plus or minus infinity times plus or minus infinity, it is equally an indeterminate form. Then everything remain the same. If you have the limit of let's say the limit of f of x being positive infinity plus or minus infinity, and the limit of g of x being a certain L prime, then upon division we are still going to have plus or minus infinity, because infinity means a very large number, a very, very large number. Alright, so now it will only depend on the sign of that large number, meaning that the sign of the infinity, be it positive infinity or negative infinity. Now we are done with mathematical operation on limits. We are done with that, and now we are going to move ahead. Let us talk about indeterminate forms. When I was presenting to you the tables, you were saying if, and now what is the meaning of that if indeterminate form? What is the meaning? In mathematics, there are 7 major indeterminate forms. But now, what is an indeterminate form? When evaluating limits, we often come to a point where we can't see the value of the limit. The form obtained is called indeterminate form. So when you come to a point where you cannot say the exact value of the limit, then that value you have obtained, that number you have obtained, or that limit is an indeterminate limit. So the form you obtained when you cannot tell the value of the limit is called indeterminate form. So in mathematics, like I said, there are 7 major indeterminate forms, which I am going to present to you. 1, 2, 3, 4, 5, 6, 7. You have 0 over 0, you have infinity over infinity, plus or minus, you have infinity minus infinity, 0 times infinity, 0 to the power 0, 1 to the power infinity, and finally infinity raised to the power of 0. Now in mathematics, we know that any number raised to the power 0 is 1. Of course, is 1. So does it mean infinity raised to the power 0 is 1? Okay. Does it also mean that 0 raised to the power 0 is 1? Okay. So now equally, does it mean that 0, we know when you divide a number by itself, you should have 1. For example, we have 2 on 2. If we divide 2 by 2, we have 1. If we divide 3 by 3, we have 1. Does it mean 0 divided by 0 will be 1? Alright, so these are indeterminate forms. If you subtract a number from itself, you have 0. Let's say 2 minus 2, 5 minus 5, you have 0. Does it mean infinity minus infinity is 0? No, because this infinity, we don't know the value of the infinity. Infinity just means a very large number, but we can't tell the value of the infinity. So infinity minus infinity, we cannot tell. It is not necessarily 0, and therefore it is indeterminate form. Any number times 0 is 0. Doesn't mean 0 times infinity is 0. It is indeterminate. So these are the 7 indeterminate forms in mathematics. All right, so in the next slide, I am going to be presenting to you standard limits. There are some limits whose value are standard, and we can equally use this standard limit to actually find the value of other limits. You just take, for instance, those who love chemistry, or you can use a standard solution to titrate a solution of unknown concentration. So we're going to be able to use this standard limit to find the limit of other limits, or find the value of other limits, or to find the limit of other functions. All right, very good. Now we're going to, this is the first standard limit. The limit as x tends to 0 of sine x on x is 1. Now you notice if you fit the value there, you're going to have 0 and 0, because sine 0 is 0 and x is 0, so you have 0 over 0. And remember, 0 over 0 is indeterminate. Yeah, it is indeterminate. But now as a standard limit, the limit as x tends to 0 of sine x on x is 1. The limit as x tends to 0 of tan x on x is also 1. The limit as x tends to 0 of ln of 1 plus x on x is 1. Then now the limit of as x tends to 0 of e to the x plus 1 on x is 1. Now the limits in the form of 1 raised to the power of infinity. Yes, we have limit as x tends to 0 of 1 plus x, or that raised to the power of 1 on x. So we have 1 plus x. As x tends to 0, by direct substitution, we are going to have 1 plus 0, which is 1. And then the power, we have 1 divided by 0. And 1 divided by 0 is provided 1 is positive. Alright, so we're going to have 1 divided by 0 as positive infinity. And now we have the limit as x tends to 0 of 1 raised to the power infinity. And this is e by standard limits. Next, we have that the limit as x tends to infinity of 1 plus 1 on x raised to the power x. So 1 plus 1 on x, as x tends to infinity, 1 on x tends to 0. If you take 1 divided by a very big number, you're going to have a value very close to 0, so it tends to 0. So at the end, we're going to have 1 raised to the power of infinity, which is still e. Alright, okay, in this case now, in the third one, we have limit as x tends to infinity of 1 plus a on x. A on x, and x is what? Infinity. So we have a on infinity raised to the power of x. X is infinity. So now we are going to have 1 plus a on x. We don't know the value of a here. Yes, in this case we don't know the value of a. And infinity signifies a very big number. So in this case we are going to have e raised to the power of e. Okay, I continue with the standard limits. We have that the limit as x tends to 0 of 1 minus cos x on x is half. We have that the limit as x tends to 0 of 1 plus x, all that raised to the power n, then minus 1, all that divided by x is equal to n, which is the power. But for this to happen, n must be a real number. Also, the limit at x tends to 0 from above of a of x to the power a times ln x to the power b is equal to 0. And for this to happen, a and b must be positive numbers. Alright, next, the limit as x tends to plus or minus infinity of 1 plus a on x, or that raised to the power of x is equal to e to the a, provided for every a which is real set of real numbers. Alright, okay, we're going to look at another case study. We're going to look at a case study. Let's take for instance that f of x is far greater than g of x. So if f of x is very greater than g of x, then the limit as x tends to a of f of x over g of x is plus or minus infinity. When will it be plus and when will it be minus? It depends on the sign of f of x and g of x. So provided f of x is always greater than or very greater than g of x, then the limit of f of x over g of x is positive or negative infinity. But the other way around will be 0, that the limit of g of x now, the smaller function, the function that is far smaller than the denominator function f of x, then now the limit will give you 0. Alright, we now get here to the method of removing indeterminate form. Sometimes when you evaluate limits, you may get to a point where you have an indeterminate form, and when you get to this indeterminate form, how do you resolve the indeterminate form? Limits are generally evaluated by direct substitution. And what's the meaning of direct substitution? You just fit in the value such that if you have the limit as x tends to a of f of x, you just fit in a and you have f of a. But the only condition under which you can do this is that a must be an element of the domain of the function. Then you can just do direct substitution. But sometimes when you do direct substitution, you may end up with an indeterminate form. Then the first way of resolving an indeterminate form is L'Hopital's rule. L'Hopital's rule. I have omitted an E. L'Hopital's rule. And L'Hopital's rule can only be used for rational functions. So it is a rule used for rational functions when direct substitution gives the indeterminate form, and the specific indeterminate form we have 0 from above or from below divided by 0 from above or from below. I'm saying from above or from below, meaning that any one of them, and also plus or minus infinity divided by plus or minus infinity. When you have any of these four, there are 4 of them because I've compile them together. There are any of these 4 indeterminate forms can be resolved by L'Hopital's rule. Now, if in case you evaluate a limit and you have one of these indeterminate forms, then in order to resolve the limit by L'Hopital's rule, you have to differentiate the function in the numerator and the denominator. So the limit as x tends to a of f of x or divided by g of x is the same as the limit as x tends to a of f prime of x divided by g prime of x. What is f prime of x? The derivative of f, and g prime the derivative of g. If it still gives you an indeterminate form, you can differentiate the second time. Now you have the limit as x tends to a of f double prime of x divided by g double prime of x. If it still gives you an indeterminate form, you continue, you differentiate again the top and the bottom, and you still fit in, and then all that until you receive a determinate answer. You receive a response that corresponds. All right, so that is it. That's all about L'Hopital's rule. Let us now look at an example. This is summary. This is summary of what L'Hopital's rule says. Now let's look at an example. In summary, provided f of a is not 0 and g of a is not 0, then the derivative, then the limit as x tends to a of f of x over g of x, if it gives you 0 and 0, then you can resolve the limit by the derivative of the top and the bottom. So this is what we have to say in summary for L'Hopital's rule. But now that is not the only way to resolve indeterminate form. We can equally use the change of variable. Why do we use the change of variable? In order to obtain a standard limit. Remember, I have presented to you some standard limits. So in case when you have an indeterminate form, you have done direct substitution of a limit, and you have an indeterminate form, you can use the change of variable in order to obtain a standard limit. So the main objective when carrying out the change of variable is to have a standard limit. The change of variable is done with the aim of obtaining standard limits. So now I leave you with an exercise. I will welcome the solution to this exercise to my WhatsApp group. WhatsApp chat. It's not in the group. Send it to me privately. 675802416. I will welcome your own solution there, but I will come up anytime soon with the solution. Alright, so evaluate the limit by using the change of variable. So like in number 1, we have to change the variable in order that this function should resemble a standard limit function, so that we can determine the limit of this function. Alright, I think that we can continue now with this important theorem, this very important theorem in the study of limit. It is known as the sandwich theorem or the squeeze theorem. So sometime you can equally resolve indeterminate form, or you can equally find the value of a limit by using sandwich theorem. So it has so many names: sandwich theorem, the squeeze theorem, or the gendarme theorem, or the two policemen theorem. Why all these names? I will try to explain a little. This is a method of evaluating limit by comparison. We simply compare this limit with two other limits, and these two limits must be to the right and to the left of the limits whose value we are finding. So provided the limit of the function to the left of it is equal to the limit to the function of the right, then that limit will be equal to the limit of the function in the middle. So this is the summary. Let f be a function defined on an interval I. If for every x belonging to that interval there exist two functions g of x and h of x, such that f of x lies in between g of x and h of x, then the sandwich theorem will state that the limit as x tends to x naught of f of x is equal to L if and only if the limit of g of x is equal to the limit of f of x and is equal to L. So now you notice that f of x is in the middle. F of x is in the middle, and since the two functions to the left and to the right of f of x have the same value of limit, then we can conclude that that is the same limit for the function f of x. Now if the limit of g of x and h of x are not the same, then the limit does not exist. So now, why do we call this the Gendarme theorem, or the sandwich theorem, or the squeeze theorem, or the two policemen theorem? I'm going to explain with the policemen. So in this case, the policemen are g of x and h of x, and f of x now is the bandit or the thief. So imagine two policemen coming to arrest a thief. When these two policemen come and arrest a thief, the thief will be in the middle of the two policemen, and the first policeman will be at the left and the second at the right, and the thief will be in the middle. Where are they taking the thief to? The policemen are going to the cell. They are going to the police station. It means if they are going to the police station, the thief who has been arrested must also be going to the police station, not by his likeness though, but he has to arrive the police station. He has to get to the cell. So this is what happens here. Provided that we have two people that are going to the same destination, then you in the middle, you must also follow them to where they are going to. So g of x and h of x have the same limit. Finally, f of x being in the middle of the two of them must have the same limit as well. Alright, ladies and gentlemen, we can also resolve indeterminate forms of limit by the use of conjugate expression. Here we multiply both the numerator and the denominator by the conjugate of the third in the function. Each time we apply this technique, we must recognize that the square root of x squared is equal to the absolute value of x. So the square root of x squared is not equal to x, but rather it is equal to the absolute value of x, which must be positive. So it is now when you put the absolute value of x, it means it has two definitions. For x greater than or equal to 0, it is positive, and for x less than 0, it is negative. But when you put the absolute value there, it means the outcome must always be positive. So that's why it has two definitions. Now I am also leaving you with another exercise. I named it example because I thought I'm going to do it out with you, but now I am going just to leave it with you. Do it actually, and send your solution through the comment section or to me on WhatsApp. Alright, we continue. Ladies and gentlemen, I believe the tutorial has been of help to you, and that it has been able to solve most of your challenges, your problems in the theory of limits. Or if you have been facing challenges in curve sketching, do well to go through the tutorial again, and stay tuned to the video, to this channel, because I shall upload new videos as well to continue part 2 and the whole of curve sketching. So if you're having challenges in these areas of studies, stay tuned to the channel. Subscribe, turn on your notification so that you shall be notified when I upload these videos, so you come and watch them. For those who are preparing for the GCE ordinary and advanced level, or especially advanced level in the subject or further mathematics, this video is going to be of good help to you. For those who are going in for competitive entrance examination into professional schools, I mean concours concerning engineering, polytechnic, or FET, école de travaux, we have SUPTIC and all the other engineering concours. This video is actually an essential into polytechnic. Alright, so that was it with Engineer Godwill Yakum. See you in the next video.